Hello everyone, this is Gokul Alex. Welcome back to my YouTube channel. Today we are continuing our conversation on the marvels of cryptography. The Cryptography Chronicles series is focused on unraveling the mathematical methods used in the modern maze of information. Today we will go through a very exciting concept known as bilinear pairings. It is one of the most beautiful cryptographic concept used in elliptical curves. It's essentially a multiplicative method on elliptical curves. Let's start our deep dive on bilinear pairings. Before delving deep into bilinear curves, it is important to understand the emergence of elliptical curve cryptographic techniques or study about elliptical curves or even the historic origins of elliptical functions. When we look at the mathematical origins, the concepts were originally connected to the problem of calculating arc length of eclipse and lemniscates. We are depicting, you can see the eclipse and the lemniscate below. So this problem resulted in the development of impossible integrals that had no solutions in standard calculus in those times. And these complex integrals challenged the mathematicians, brilliant mathematicians of those time. And then later on, it was Carl Gustav Jacobi and Abel. They have come up with an ingenious solution. As you see here, the arc length integral is relatively complex. Instead of computing the integral directly, both Jacobi and Abel came up with a method for computing the inverse functions. Let's try to understand the core concept behind these inverse functions. It was in 1829 when Carl Gustav Jacobi published his masterpiece on this. He and Niels Henrik Abel had the revolutionary idea to invert the problem. Instead of studying the integral value, they studied the inverse functions. They are now known as elliptic functions. You can see the inverse operation, how geometrically it is different from the integral functions. So the blue path shows the complex integral. The red path in the diagram shows the inverse function, which is finding point z from the arc length s. Okay, so Jacobi realized that these functions were doubly periodic, meaning they repeated themselves over a grid. Now we can call them as lattice. These grids are computed over in a complex plane. So this lattice structure is known as Jacobian variety. So one major challenge with this Jacobian variety is that it has to be computed on complex plane. So while Jacobi defined it over a complex number, this definition did not work well for the finite fields. As we all know, finite fields are used in modern cryptography. This constraint was addressed by another mathematician called Andre Weil. Right now, we are in this diagram, we are seeing the depiction of elliptical curve and associated target group, which we will try to understand in the coming slides. So till the previous slide, we were trying to understand the historic origins of the elliptic functions. and they were not very useful until Andrew Weil came up with his method, how from complex numbers to the world of finite fields. So in his approach, he completely reconstructed the Jacobian as an abstract algebraic variety. He proved that you could build a group structure just by using polynomial equations alone without needing complex numbers. This was a massive achievement, a milestone. So Andre Weil introduced Weil pairings. This is where we are only looking at the pairing, bilinear pairings or pairing in elliptical curves. He introduced the Weil pairings in 1940, working on the elliptical curves and abelian varieties. Later, in the early 1960s, it was John Tate who introduced the duality ideas that led to the Tate pairings. So what are these pairings? This core concept of this pairing is we need to map points from elliptical curve to a target group. If you multiply a point in an elliptical curve by a scalar on the curve, the result of the pairing is raised to the power of a target group. This is the core concept. As you see in this diagram, if we multiply a point in the curve, let's say the point P, and when you multiply it by a particular scalar, let's say 2, then you will, it will result in an exponential operation, as we see in this equation, but that is equivalent to doing a multiplication on the target group. So as you see here in this diagram, you're adding point P, and the left subplot you can see you're adding the point P to another point, the same point P. So it's like a doubling operation. And when you're adding it, it is equivalent to hitting the curve at minus 2p, that is reflected into the point 2p on the other side. This represents the scalar multiplication by a factor of 2 for the point P. So what we're seeing is a multiplication operation, and which it is represented on the right side as a circle, as a group GT. It is of these target groups are often the roots of unity in a finite field, and where the operations are multiplicative. Let's understand how it happens in the group. The point, what we see here on the geometric circle, is EPQ, the point with the red arrow, and this is the result of pairing point P with another point Q. The elliptical curve point 2P and with Q is shown with the green arrow. It is the result of pairing the double point or the scalar multiplied point 2P with Q. Because of the bilinear property, this value is exactly the square of EPQ. So what is the inference? Squaring a complex number on the unit circle, as we know, it's shown with the squaring a complex number in this circle double its angle. The green arrow E to the 2PQ is exactly twice the angle of the red arrow. So the green arrow is twice the angle of the red arrow. So this property allows cryptographers to verify the relationship between hidden numbers. Let's say if we know there are points P, another point, the multiplier of the point P with the scalar A, there is another point P, the multiplier of multiplying the point P with a scalar B. it's not easy to find A or B. That's a discrete logarithm problem. But using this pairing property in the elliptical curve, we can verify the fourth point, A, B, P. A, B is the scalar multiplier to the point P, as per the expression shown below. The elliptical curve point, the point APBP is equal to the elliptical curve points with the exponential, which is equal to the another point, which is EABP with P. So what is the benefit of this? When you are when you are easily able to do a discrete logarithm operation with multiple scalars, you are able to create the relationships with multiple points. So this is the benefit of the operation, which has been used in a lot of elliptical curve cryptographic implementations, mainly in we see in zk-SNARKs, the zero knowledge proof implementations in Zcash, or the use of BLS signatures in Ethereum 2.0. Now we come across a very ingenious technique invented by Victor Miller in 1986, which helped us to realize this beautiful concept. It is known as Miller's algorithm. Victor Miller conceptualized in 1986 that Weil pairings or Tate pairings can be evaluated by constructing and evaluating certain type of rational functions on the elliptical curve. So these functions are known by Miller algorithm name. Essentially, what is this rational function? To compute a pairing E with P and Q, we need to evaluate a function f of n at a point Q. This function is defined by a massive divisor where n is a large prime. This is the problem at hand. The issue is that the degree of the function is n, which is a large prime. If you try to write this function as a polynomial ratio, the exponent will be astronomically large. So how Miller circumvented this problem? Victor Miller realized that we can construct the function f of n step by step using double and add method, similar to how you compute scalar multiplication efficiently. So this method, by doubling and adding in an iterative method, is what Victor Miller has implemented. So instead of computing f of n directly, we can compute a sequence of smaller functions, f of k, that builds up f of n in a recursive relation. That relation is constructed using a smaller function called f of k together with a tangential line function and a vertical line function. So every step in this algorithm involves two geometric lines, a tangent or a chord, and a vertical line. As you see in this diagram, you can see a tangent to the elliptical curve and a vertical line. These lines correct the divisor as we double and add points. Pretty ingenious and intuitive technique. So today we covered some of the core concepts powering the elliptical curve cryptography, starting from the historic origins in the pioneering work of Carl Gustav Jacobi and Niels Henrik Abel. And then we touched upon the Weil pairings and Tate pairings. And then we have summarized how this pairing-based cryptography works, understanding the concepts. And then we went to, we had a brief tour on Miller's algorithm. Thank you so much for watching this session. Please share this video in your circles and subscribe to the YouTube channel. Thank you so much, everyone.